Hello and welcome to another lecture with the topic of the extreme value theorem, which we're going to be calling EVT. This is a very short summary of what it's about, really. Find the derivative, set it equal to zero. We're going to see why we're going to be doing that. So the goal today is, this is one of the most important applications of the derivative. Given a function on a certain domain D, we want to be able to find the smallest or largest value of the function over that domain, or maybe over some smaller piece, if they actually exist, because there are functions that don't assume their largest or smallest value. And even before we do any theory over this, I just wanted to show you an introductory example that's going to illustrate the main idea of today. Here it is. Consider this function. It's a cubic polynomial and a graph below. So I have a sketch for the graph. So the values that I'm calling R and S in this graph, they are not actually the largest or smallest values of the function f. As you can see, f is, it has a limit of minus infinity if you go towards minus infinity, and plus infinity on the other side. So it does not actually have a max or minimum value. However, these values, they still have significance. We're going to be calling them locally largest and smallest. I hope you can agree with this statement that around this point x1, r is the largest value that the function has. And similarly, around the point x2, s is the smallest value. So they have some significance in problems where you have applications. Well, this type of locally maximum and locally minimum value, they have significance. So you want to be able to find them. But how do we compute them? So this is just an example before we do the theory. The idea is that if you look at the graph, you should get the intuition, and that intuition would be correct, that the tangent line around those points is horizontal. The fact that the graph is attaining a locally maximum or locally minimum value means that if it has a tangent line there, then it must be horizontal, which means the derivative is equal to zero at those points. So this is what we know about those points. F prime of x1 and f prime of x2, they should be zero. And this gives you a recipe to finding those values. Well, at least finding x1 and x2 first, but then you can find r and s because those are the values of the function. So what we have to do is, first of all, compute the derivative, f prime, and then set it equal to zero to find x1, x2. This derivative is an easy one. So I'm just going to differentiate the polynomial here. X cubed becomes 3x squared. The x squared term will bring because of the power rule, this 2 is going to go outside, multiplying the fraction 9 over 2. So that's just going to give you minus 9x. The 6x, the derivative of that becomes 6, and then the plus 1 has a derivative of 0. So now this is the derivative. Set it equal to 0 and solve for x. Well, we can divide by 3 here, just simplify, and you see that the solutions are 1 and 2. That should be correct, yes. So as you can see from the graph, we already knew from the graph there would be two solutions, and we indeed find the two of them here. So this is 1, this is 2. And now what are r and s? R is the value of the function at this point 1. So just compute f of 1 by the formula given for the f function. It was x cubed minus 9 over 2x squared plus 6x plus 1, I believe. Yeah, this is right. So anyway, whatever this is, you have an 8 minus 9 over 2, so 7 over 2. That's r. And s would be 2 cubed minus 9 over 2, 2 squared plus 6 times 2 plus 1. So that's 8 minus 18 plus 12 plus 1. What is that? 21 minus 18, that's 3. Also, according to the graph, we already expected the S to be slightly less than R. So I'm just double checking the numbers that I found. It makes sense, right? S was supposed to be a little bit smaller than R. This is actually what we are finding here. So this example illustrates the idea of how we're gonna be finding these values and also the points where they happen. So before we can get to that, get to problems, we're gonna need to go through a good deal of terminology. A lot of the future slides now here are gonna have just terminology, new terms that we need to know what they mean. And you have a lot of copying down to do. I'm gonna have some big boxes here introducing certain terms that we absolutely need to know, but they should be very easy. So we're gonna spend a good chunk of time now going through very simple graphical examples to illustrate all of this. But first of all, just an English remark. We're gonna be using the words maximum, minimum, extremum as nouns. Those are objects. Those are points that we can talk about. And the plural forms of these words are maxima, minima, extrema. So not that anyone cares when you write them on an exam. You're not going to lose points if you write maxima for a singular point, but it should be maximum. So just so you are aware. All right. So our first definition here is about global values. So first of all, the words absolute and global are always going to be used interchangeably. I'm going to prefer global, but you may see absolute being used as well. So just remember they mean exactly the same thing. All right, but let's read the definition. So let f be a function, let a be some subset of the domain, which is usually going to be an interval, this little a here, or this big A. So what we're going to be calling global maximum value, the global maximum value of the function over A, if it exists, it is the number, the value f of c with the property that it is larger or at least equal to any other f of x for x in this set A. So it is exactly what the name says. It is the largest possible value of the function, the largest possible f of something over that interval A. That's why we call it global maximum, because it's over the entire A. Similarly, there is the concept of the global minimum value. It's exactly the same thing, just reverse the inequality here. It is the number f of d that is smaller than or equal to any other f of x. And finally, the an absolute extreme value or global extreme value. This should have been in bold face here instead of italic. If one exists, it is a value that is either global max or global min value. So we're always going to have this as well. We're going to be talking about maximum and minimum. And then if you have an object that's either one of them, you can call that object extreme. So let's just go over a few graphical examples, and we can make sure that we understand what is meant here. The key idea is that the word value means the values of the function. So it means that you're going to be looking on the y-axis. Those are the values of the function. So consider this graph. Over the set from between 1 and 6, this is the set A that we were talking about in the definition. So over this set between 1 and 6, what is the global maximum value of the function? So we're looking at the entire piece of this graph. The maximum value that it attains over the set is right here, 50, because it is attained at the number 2, f of 2 is 50. So that value is 50. And similarly, the smallest possible value that you can find is 10. That's the global minimum value. So finally, what are the global extreme values? There are two of them. It is both of those, 10 and 50. If it is a maximum or a minimum, then it is an extreme value. So this is what it is. This is what we're doing here. But now it's still referring to the same graph. This concept of global min, global max, it depends on the location where you look. So now if you're just going to look over the set between 3 and 6, what happens here? So now you're just looking at this piece of the graph down here. What is the global maximum value? The maximum value you can find between 3 and 6 for f of x is now 30. And 30 is actually attained at two different locations. It is both f of 3 and f of 6. Meanwhile, the global minimum value you can find is still 10. It is still f of 4. So those are the global extreme values over this piece between 3 and 6. So let's move on to some other examples here. This function now, it has a vertical asymptote at x equals 6. This is what the graph is trying to convey to you, that it's becoming vertical at that point. So now let's consider this function over the set between 0 and 5. What is the global maximum value you can find? If you're only looking between 0 and 5, you see the graph is increasing over that piece. The maximum value you can find is f of 5, which is 50. And the minimum value you can find is f of 0, 20. Those two values are global extreme values, 20 and 50. But what's going to happen now in the next piece, over the set between 3 and 6, notice that my interval is open at 6 because this piece is supposed to be part of the domain of the function, and 6 is not in the domain of the function. There is no value for f of 6. So that's why I had to exclude the number 6 here. But anyway, over this piece, there is no global maximum value. That, remember, I told you this is a possibility. The function between 3 and 6, it just keeps increasing without bounds. No matter which value you select here inside 3, 6, it's going to have some very large value for f of x, but you can always find even larger ones. So there is no maximum value. However, there is still one global minimum value between 3 and 6. It is f of 3, which is 30. So what are the global extreme values over this piece? There is just one. There is just 30, and it is a minimum value. I hope this is really not that bad, not too difficult. Just one more example of these guys. Now I'm giving you a function that has a discontinuity here. The value of f of 4 is not the limit. It is a little below the limit. So what is happening here? Over the set between 4 and 7, including both. What is the largest possible value you can find here? Between 4 and 7, it is up here. We don't know exactly what the x coordinate is, but the value is 60. And what is the global minimum value? Well, f of 4 is all the way down here. And there is no other values below this guy. That's the global minimum over this piece. So it is a 10. So the global extremes are both 10 and 60. But now let's change the piece. Let's change the location where we look. The piece that I told you is usually an interval. It might also be something like this, a union of two intervals. So now this is the set that goes between 1 and 7, but excluding the number 4. What is the global maximum value you can find? It is still 60. This time it is attained at two different locations down here. That doesn't matter. There is just still one value of 60. But what is the minimum? The answer is there is no minimum now. Remember, we are excluding the number 4 from this piece. So the smallest locations on this graph that you can find, they're kind of down here. They're converging down towards the number 20. But there is no single smallest one. If you take a number really, really close to 4, the value of the function here is going to be really, really close to 20, but still above 20, like 20.1, for example. This is indicated by the fact that the graph is going down towards that point. But there is no single smallest one. 20 itself is never attained. And then the global extreme values over this piece, that will be only the number 60. Okay, so what we've done so far, we've talked about values. That means the numbers on the y-axis. In the next slide, we're going to be focusing now on the points. Points means usually the numbers on the x-axis, but the concepts are going to be exactly the same. So now, once again, let f be a function. Let a be some subset of its domain, usually an interval. So now we're discussing points. Still absolute or global, but points. What is a global maximum point of f over a? If one exists, it is a number such that f of that number is the global max over that set. So it just means the x coordinate of the global max value. I should probably have included the word value here that for clarity. Global max value, global min value. Right, so in the second piece here, it's the same concept, but for a minimum, a global minimum point is a location on the domain where f of that point is the global minimum value of the function. And finally, extreme, global extreme point. Once again, this should have been in boldface. What does that mean? It means a point that is either a global max point or a global min point. So examples again. Here is a function that once again has a vertical asymptote. Let's look over the set 1, 5. So stopping at 5 here. What are the global maximum points? Now this time you're going to find the global maximum value, which is 40. And then you look at what are the points where that value is attained. And there are two of them. There's 1 and 4. So you can see that there can be more than one point now, which is not the case for values. Global minimum points, what are they? We're looking only between 1 and 5. Well, there is only one place where this minimum value of 10 is attained, and it's at the number 2. So that's the global minimum point. And what are the global extreme points? Those are the ones that are global min or max points, 1, 2, and 4. Meanwhile, over the set 2, 6, so now looking between 2 and 6, the maximum value is still 40, but now only attained at one location, only at x equals 4. So this is the only global maximum point. Meanwhile, there are no global minimum points this time, because there is no global minimum value. If you're looking between 2 and 6, the function is going down forever as you get closer and closer to 6. There is no minimum. So there's only one global extreme point, only the number 4. And finally, I have a quick word problem here. Instead of giving you the graph, I'm giving you the function. If f of x is the function 5 minus 2x, find all the global extreme points and values over the following two sets. So 0, 3 closed and 0, 3 open. So basically what happens here is that, let's only look between 0 and 3. This is a linear function. It crosses the y-axis at the number 5 up here, and then slope of negative 2. So what is the what is f of 3? That's actually 5 minus 6 minus 1, right? So we have to keep going a little bit into the negative numbers. But anyway, this is the graph of the function between 0 and 3. So if you are considering this function on the domain 0, 3 closed, then you can see there are two locations where a global maximum and a global minimum exist. right? Because f of 0 would be 5, that's the maximum possible. F of 3 would be -1, that would be the minimum possible. So the answer for item A, I guess it fits in here, global max value is 5, global min value is -1. But they were now also asking for points, not only values. What are the points? Global max point is 0. F of 0 is the one that gives you 5 right here. And then global min point, the x coordinate where the global min is attained is 3. F of 3 is -1. But the answer to item B is D and E for both extreme points and values. If you are now with an open domain between 0 and 3, well, in that case, you are actually excluding these two extremes. The graph is only really the piece between the two of them, and it never reaches the maximum of 5 or the minimum of -1. It just keeps getting closer to them. But there is no single largest or smallest value for the function. So just illustrating the fact, once again, that these concepts depend on the domain, on the set where you're looking. So now we are finally in a position to talk about this EVT, extreme value theorem. What does it say? It's very simple. If you have a continuous function, then over any closed interval, there must always exist a global max value and a global min value. This theorem, it is, if you want to actually prove it by doing some formal, rigorous arguments, you need to also have a formal and rigorous definition of continuity and limits. By consequence, we don't actually have that in calculus, so we cannot provide a rigorous proof for this theorem. But I believe it's an idea that we should believe it, that we should think it's very intuitive. The first picture here is supposed to illustrate that, but always remember there are these two important hypothesis. The function is continuous and you're looking over a closed set, closed interval. So in the first picture, what happens? Imagine you have a continuous function defined on the closed interval between a and b. So the function has a value for f of a and also f of b, and it is a continuous graph between them. It might be just a line. It might actually go way up and then down to b. It may oscillate like this, but whatever you do here, I hope you can see that you're always going to attain a maximal and a minimum value, whatever you do. In the case of the line, those were at A and B. In the case of a graph that goes way up there, then the place where it turns back down is the global maximal, but that place exists because of continuity. Meanwhile, in the second picture here, I'm just showing you that if you have a discontinuous function, then it doesn't actually need to have a global maximal or minimum. Look at this one. This function is defined between a and b on all points. Even at this point of discontinuity, there is a value for the function. But you can see this function does not have a global max. It kind of wants to be this number up here, but it does not actually attain that number. So if you have a discontinuous function, it's possible to not have a global max or min inside of an interval like this. And finally, also illustrating here the importance of the interval being closed. This time I have a continuous function, but only on the open interval a to b, and it obviously does not have a global max because, well, it wanted to be that point up there, but when it got to there, there was no value for the function because it was not defined at b. So this function does not have to have a global max or min, even though it does have a min in this case, but no max. This is the EVT then. It's a reassuring fact that most of the functions that we encounter, even in real world applications, they are continuous. So if you want to find the largest and smallest values of them, because that's going to be useful for you, then you can be assured they exist. So that's good to know. Remark, sometimes here's the plural form of the word extrema. The global extrema over an interval, sometimes they happen only inside of the interval. Other times they might also happen at the end points. That's like the A and the B in the interval. So just quick examples here that you should be aware. In the first one, I have a function that has a global maximum point only inside of the interval, the open interval AB. The global maximum point is right here, right? Because that's the location where the function is at its global maximum value. In the second picture, the global maximum point is actually only A and no other points. This is where the function is at the largest value. And in the third picture here, I'm showing you an example where the global maximum point happens both at one of the endpoints of the interval, the number A, as well as inside whatever this number down here is. That's also a global maximum point. Okay, what is next? Yes, so now we finally finished discussing this idea of global things. We're now going to turn to local things. It is very similar. Local just means that you're not looking over the entire set A. You're just looking around the point. So take a function f, take some interval closed between A and B, a local maximum point. Point is the word here, and then we're going to say value later. So a local maximum point of the function over A, by definition, is a number in the inside, in the open interval, such that f of c is larger than the f of x's. This time not for all x's, but only for the x's that are close to it. This is what qualifies this as local, because it's only the points which are close to it. And in that case, the value f of c is called a local maximum value. Similarly, a local minimum point, once again, local, close. It is a point, well, it is a number d in the open interval. I'm going to leave this underlined here, that's important, such that the value of the function there is smaller than or equal to the other values around it, so for points close to it. And in that case, the value is called a local minimum value. And you can probably guess, what does local extreme point mean? It means a point in the open interval that is either a local max point or a local min point. In that case, the value of the function is called local extreme value. So anyway, more examples, just one actually. Well, I have two. For us to see this very clearly. So kind of an oscillating function here. What are the local max points? So this time you're not looking globally. I mean, it's zero only considering the points between 0 and 7, but you're not looking at the entire graph. There is no single maximum over the entire graph in this case, but what are the local ones? So the points around which the function is at a maximum. So you're looking at these peaks on the graph. Well, this one right here is not a peak because that's not the value of the function up there. So only the first two. Those are local max, you can say like locations. The points corresponding to them are 2 and 4 down here. And the values would be 70 and 90. Those are local. What about minimum? Local minimum points. Those would be, remember, only inside. So you don't consider 0 or 7. You don't consider the endpoints of the interval. You only consider inside, so the open interval between 0 and 7. You're now looking at the points where the function is at a valley. So like this one, and also this one right here. The value of f of 6 is smaller than or equal to any other values around it. That is definitely true in this graph, so it counts. Anyway, so the minimum points locally would be 3, 5, and 6 with the corresponding values of, so f of 3 is 40 and so on. 40, f of 5 is 60, f of 6 is 80. All right. Local extreme points, that's either the local maximum points or local minimum points. So you consider 2, 4, 3, 5, and 6. We don't have to give them in order, just listing them and the values 70, 90, 40, 60, and 80. So this is the concept of a local extreme point and value. In this next example here, I'm also again just giving you a function without a graph, but we're going to draw the graph. What are the local max points and local min points of the constant function f of x equals pi over the set between 1 and 3? So I'm giving you this function now. It's always pi. It's a horizontal line between 1 and 3. So by looking at this function, you don't see any valleys or peaks, but just remember that a point is considered to be locally max or min if the, let me scroll back up, the value of the function at that point is larger than or equal or smaller than or equal to other values around it. That's definitely the case here for any point. Any point between 1 and 3, any x here has this property that f of x is larger than or equal to points around it because it's all pi, and it's also smaller than or equal, again, because those are all pi. So any number between 1 and 3, it qualifies as a local max and also a local min, but not 1 and 3 themselves because those are the endpoints. So the answer here, the question was asking for what are the local max points and local min points, and they're both the same. The local max points are anything between 1 and 3. Similarly for the min points. We just exclude 1 and 3 because they are endpoints of the interval. Last definition, last piece of terminology for today, the concept of a critical point. This is really the one that's going to be the most useful for us, and it's the easiest one to define. So let f be a function, a point x in the interior of the domain. So once again, if your domain is a closed interval like this, a, b, you're only going to consider those between a and b open. So a point like that is called a critical point of f when one of the two conditions below happens. Either the derivative is 0 or the derivative does not exist. So I'm displaying a few examples here, both x1, x2, x3. All these guys are critical points of this function. They are points between the a and b, which is the domain of this function, where either the derivative does not exist right here because of the cusp, or the derivative is equal to 0, horizontal tangent line. Those are called critical points. Why do we talk about those? There is a theorem, local extremum theorem, due to Fermat, very early, like maybe 1600s or 1700s, but it says that if you have a local extreme point, either max or min, and the derivative exists, then the derivative must be 0. So another way to say this is that if you have a local extreme point, then it must be a critical point. I think it's pretty self-explanatory if you try to think about this theorem. Once again, this connects back to the example in the beginning of this lecture, but let's look at this graph up here again. What are the local extreme points of this graph? It is precisely these three guys. You have two local minimum points and one local maximum point. And you can see that the only way that that can happen is those two conditions that qualify for a critical point. The only way, if the function is differentiable, then you must have this horizontal line. There's no other way for the graph to start having a local maximum point up there without going through a horizontal line like that. If it is differentiable. Then if it is not differentiable, I mean, then sure, it can still happen like this. You can have a corner. That's the way that the graph managed to have a local minimum in here. So what do we take from all this? We take the following. This is, I guess, the most important box to remember. If you're searching for the local extreme points of a function, basically look for the critical points. Look for the places where the derivative is 0 or does not exist. Those are the only possible locations where you can find a local extreme point. Meanwhile, if you're looking for global extreme points, well, they have to be local as well if they are inside. I hope you can agree with that. Like if it is a global, meaning the value of the function there is the maximum possible or minimum possible everywhere, then it has to be local as well. It has to be true around the point. So if you're looking for global extreme points, look for the local ones, which means look for the critical points, as well as this time also the end points. We're going to see examples and then remark not all critical points are going to be local extreme points. Just because you found a critical point, that does not mean it's going to be an extreme. You can have functions that do things like this. The tangent line tries to become horizontal at this point. It becomes horizontal, but then the function continues to decrease. So imagine something like this with a horizontal tangent line at that point. Even though this point is a critical point because the derivative is 0, it is not actually a local extreme point. This is not a peak or a valley on the graph. The graph just kept decreasing around this point. So that can happen. Not all critical points are local extremes. So that was the theory for this. We don't have much time for many examples, but we can do a few. And you can see finally how this all gets applied. The first example here, find the critical points of this function, x to the x, in the domain, open domain between 0 and infinity, and find the corresponding local extreme values. If you have a critical point, and if it is actually a local extreme point, then there is a corresponding local extreme value, the value of the function. And they're also asking, are they going to be global or just local? See the graph below. So this is the graph of the function x to the x, by the way. Even though it's not defined at 0, but the limit is 1. That's something that you can try to prove. It's not so easy, but not so hard. So anyway, just keep in mind this graph. The function is x to the x. And the domain is 0 to infinity open. The question was first of all asking for find the critical points. So let's do that. Critical points. What does that mean? It means either f prime equals 0 or f prime does not exist. So we have to find f prime just to see what happens. What is the derivative of x to the x? We've done this one before. This is a case where you have to apply logarithmic differentiation. I'm going to do that in here very quickly. Basically, you take ln of f of x first, and when you differentiate, the derivative of ln of f is always f prime over f. And on the right side here, we need to apply the product rule. That's what I've just done here. I'm going to simplify x times 1 over x as simply 1. So f prime, solving for f prime, is going to be f of x times ln x plus 1. And now you can replace f of x with what it actually was. It was x to the x. This is f prime. There are no places where it does not exist. in the domain. Remember, the domain was between 0 and infinity. So we can say f prime of x exists for all x in this domain, because there are no problems here. You can if you have positive numbers, you can find the number raised to itself. You can also find ln of x. So no problems with the definition of this derivative. So that's not how we're going to get critical points. There could be a point where the derivative does not exist, but that was not the case. But what else can happen? For a critical point, it's where f prime equals 0. Let's solve for that. When is this 0? Well, either x to the x is 0 because you have this product here, or ln x plus 1 is 0. The first condition here is never going to be satisfied. Maybe a red x here so we don't confuse this with x. You cannot have a positive number raised to itself be equal to 0. That's going to be also a positive number. But at the second one here, we can solve this equation. Ln x equals minus 1, taking the exponential e to the minus 1, or also 1 over e. This is going to be the only critical point. X equals 1 over e. All right, so we found just one critical point. Let's look back in the graph now. Remember now, the question was asking for, let's go back. Find the corresponding local extreme values, and I guess points as well. We don't know yet if this is a local extreme point, but by looking at the graph, we know that there must be one. This right here is a local extreme point and value. Looking at the graph, we know there is exactly this one, right? This is the only place where the graph has a valley. So it must be the one that we found. It must be 1 over e. Again, this is the Fermat's theorem that says if you have a local extreme point, then that must be a critical point. And we just found a critical point, 1 over e. So that must be it. 1 over e is a local extreme. We even know it's minimum from the graph point. What is the value? Well, f of x was x to the x. So 1 over e raised to 1 over e. There isn't much you can do to simplify this. Just leave it like that. It is a number. This is the local extreme value. Also minimum. Is it global? That was the last question they were asking. Yes, these are also global. Once again, this is just by looking at the graph. Not only this was a valley on the graph, but it also is a location where the function is at its global minimum. So this value right here of 1 over e to the 1 over e is the smallest possible you can find if you're looking for the values x of x raised to x. So this was this question. I'm just going to do one more today, which is very similar. Find the critical points of, now the function is x to the 7. The domain is all real numbers. Find the corresponding local extreme values. I should add something to this. I should say if it is actually a local extreme point. So that question should be in here. We're going to find a critical point. Is it, or are they? Are they local extreme points? And if so, then find the corresponding extreme values. And are they global? But the answer will all be no, but this time it's not going to be an extreme point. We'll see that. So anyway, the first question they're asking is find the critical points. Let's do that. That means f prime either is 0 or does not exist. F prime exists everywhere in this case, 7x to the 6. But where is it 0? Well, the solution to this equation is x to the 6 equals 0 or just x equals 0. So this is the only critical point. But now, so the next question is, are they also local extreme points? Let me just go back a few slides to the remark that we had mentioned. Not all critical points are going to be local extreme points. Here's the example that I showed you. This is exactly what's happening with this function, only reversed. If you try to graph, imagine the graph of x to the 7. What does x to the 7 look like? On the positive numbers, it is like a parabola x squared, only it grows faster. And on the negative side, well, 7 is an odd number. If you raise negative numbers to odd powers, you still get negatives. This is x to the 7. So you see that even though we found a critical point, x equals 0, because the tangent line right here at x equals 0 is horizontal, that point is actually not a local extreme. We can see it from the graph. This is not a local extreme point. Because this point is not, the value of the function there is not either larger or smaller than values around it. Values on the left side are smaller, values on the right side are larger. So it's not local extreme point. There is nothing else to do in the problem. It's not a local extreme point, so there is no corresponding local extreme value. It's not going to be a global min or max, nothing like that. So this finishes the problem. Now, when we do recitation on this topic, then that's where we're going to start with the real problems, with more complicated functions that we cannot even graph, and trying to find the maximum and minimum values of those functions using all the techniques that I showed today. What we have to take from today is the names, the distinction between point and value, between global and local, and what extreme means. Extreme means either max or min. So there's a lot of also critical points, a lot of words to remember, but it's going to be very important to know exactly what all of those mean.